Good evening, folks, and welcome to the Advent of Code C++ live stream. I'm Craig, and tonight, as every night, we are going to be working through the solutions to the day's Advent of Code puzzles in C++. So, if you missed some of the videos, you can always catch up with the replays on my YouTube channel. And we will always be posting the code for these exercises up in my GitHub repo. If you're watching this on Twitch, you can find the links to all that in my channel profile. If you're watching on YouTube, links are right down in the description. So we have about 4 minutes until day 7's puzzles drop. I've got our usual setup for the day here where I have just an empty minimal C++ program here. I've already included the check and IO libraries from my little utility libraries because we wind up using those pretty much every day to read input and do assertions. And I've set up a build file that lets the Bazel build system that we're using know how to compile our program. So actually, I'll go ahead and just test that out right now. So we're using a configuration that I already set up in the toolchains directory to use the LLVM tools instead of GCC because that's just how I prefer to work in C++. And we'll be doing an optimized build. So we'll do puzzles/day07 part 1. And oh yeah, we actually have to give it a command, don't we? So I'm going to say Bazel run. So that will build it and it will run the program. Part 1, not just part. Okay, it's compiled, it's run, and it does nothing as we expect because we haven't actually written out anything yet. So last night we managed to move pretty quickly. In fact, I only did this one program for both parts. But we realized in the first part that all the fish with the same counter are identical, so we just treat it as a bucket with that number of fish in this deck, and we got to the solution pretty quickly. And the only tricky thing about the second part was that the numbers were getting so big that we had to use 64-bit integers instead of 32-bit integers. So it's possible that if we wind up with counts of things again, I might choose to just use 64-bit integers from the start rather than 32-bit. Because who knows, things might get really big again. So yeah, like I said, last night things went pretty quickly for us, but you never know. As the days go on, puzzles tend to get a little more difficult. And it's not necessarily like a linear ramp of difficulty. And in fact, that's kind of subjective too, but that's the general idea is that things tend to get harder. So you might see me get stumped one of these nights and have to struggle with it a little bit, but that's all part of the process. In fact, the challenge is part of what makes this fun. So we have just over a minute until tonight's puzzles drop. If you have any questions about puzzles or about my development process or anything that I'm doing, you can always put those in the chat on Twitch, or if you're watching the YouTube replays later, you can post a comment on the video and I'll try and answer those questions for you. Okay. Just kind of vamping a little bit in our last 35 seconds before the puzzle unlocks. We'll have our first full week. We're drawing more and more of our undersea picture here as Santa's submarine plunges through the depths in our effort to find the sleigh keys. Okay, almost ready. Here we go. A treachery of whales. Giant whales decide your next meal. And it's much faster than you are. There's nowhere to run. Suddenly, a swarm of crabs, each its own tiny submarine, zooms in to rescue. Seem to be preparing to blast a hole in the ocean floor. There's a massive underground cave system just beyond where they're aiming. The crab submarines all need to be aligned before they'll have enough power to blast a large enough hole for your submarine to get through. Thank you, crabs! So we have to help the crab submarines get aligned, and they can only move horizontally. You quickly make a list of the horizontal position of each crab, which is the puzzle input. They have limited fuel, so you need to find a way to make all of their horizontal positions match while requiring them to spend as little fuel as possible. Okay. Okay, so we need to find the position to align them all on that will use the least amount of fuel. Okay, so let's go ahead and get our puzzle input here. We'll save that as day07.txt. And now, let's see what that looks like. Okay. So first thing we're going to do is just read in the whole file. Yeah, actually we have this read comma delimited file, which I already wrote too. Might as well use that. Let's see, what did we do that? Okay, it's still a vector of strings, but yeah, whatever. We'll use read comma delimited file to read the first argument to the program as the file name. Include string and vector since we're using those. And then we'll have a vector of integer positions that we will parse all those inputs into. So we'll say for string view in the input, we're going to go ahead and use abseil simple a to I to parse from the string form to the parsed form. And then we will put that on the back of the positions vector. Okay, so that gives us all of our inputs, and I think that the answer here as to what will minimize fuel is to find the average of all of the inputs. And then, you know, if the average winds up being between two different integers, then, you know, we round to the nearest one. So, okay. So, to find the average, we will just do, you know, sum divided by the size. So we'll use the accumulate function from the numeric header, and we will say, you know what? As I was talking about, you know, big numbers, I'm going to go ahead and just do these in 64 bits right now. I don't think we really need it for this first part, but I'm just having plenty of headroom for our calculations is always a good idea. So we'll say that the sum is equal to accumulate from positions, from the beginning of positions to the end of positions, starting with 0. Okay. It's going to give us the sum. And we'll say target is going to equal we're going to cast to doubles to do this division because we want a division with a fractional part, and then we're going to use the rounding function to round it back to the nearest integer. So we're going to cast sum to double, and we're going to divide that by the number of positions, also as a double. And then that whole thing we're going to use round on to round it to the nearest integer. Okay. So that gives us our target, and now we need to come up with how much fuel it costs, which is just the sum of the absolute values of the difference from all of those. So we don't want accumulate, but I think that there is something similar that we can use. Well, you know what? I'm not going to be too fancy with the C++ standard algorithm functions. We'll just say for each position in positions, we are going to increase the total fuel by the absolute value of the target position minus that position. And then we will print out the total fuel that is needed. Okay, I think we have everything that we need here. We just need to add a dependency on the abcell strings library into our build file. And let's go ahead and run our program on this day's input. Okay, 350,163 units of fuel. Let's see if that's correct. That is not correct. Okay. Let's go ahead and take this sample input and just see how our program behaves with it, and use that as a bit of a test. Okay, so that gives 45 as the answer. The actual answer should be 41. Oh, wait. 37. Should be the cheapest. For everything to move to 2. Interesting. Because I thought that average would get us there, but maybe I'm wrong about that. Let's print out our target here and see what that is. Of course, we could, just, exhaustively search for the least fuel for all the possible positions, but that seems like a lot. Maybe we're looking for the median? I don't know. Yeah, that picks 5, which is not... I mean, I guess I can go for a brute force here and just say, we can, calculate. So we can use the same logic that we used previously to figure out what is the cheapest here. Or just figure out the cost, actually. I mean, it's this thing. And then we can just search using that fuel for target function, using the using the minimum and maximum of the positions as boundaries. So we'll say oh yeah, and that gives an iterator, so we'll dereference it to get the actual value. And then use max for the same thing, and we'll say min fuel we're going to initialize to the maximum value of int64t, so that, any reasonable amount of fuel is going to be less than that. And we'll say candidate target starts at the minimum position, goes up to less than or equal to the maximum position, and we'll increment it there. And then we'll use fuel equal, we'll say fuel is equal to fuel for target. With that candidate target. And if fuel is less than min fuel that we've seen so far, then min fuel equals that new fuel, and the target equals that candidate target. And we don't actually have to print out that target, but I'm going to go ahead and keep track of it just in case it's necessary for part 2. And you might as well print this out too. And then print out min fuel here. Okay, so let's see what that does for the test input. That's not correct. Okay. That's giving us a target 0. The target is 0, and min fuel stays at the maximum. Is min and max not working correctly? Let's see what it thinks the minimum and maximum positions are. are these backwards? I mean, I see that, yeah, the positions range from 0 to 16, but that is really weird. I really don't know why that is. Oh, you know what? Yeah, it's just comparing the initialized. I'm sorry, I'm using not the correct thing. We want min element, not min. Um, and max element, not max. Yep, because it was just comparing the iterators themselves. Okay, so that gives us correct results for part 1. Let's run it for part 2. Or, not, excuse me, let's run it for our actual input for part 2. So, let's try that. Okay, we got that. Crabs don't seem interested in the proposed solution. Perhaps you misunderstand crab engineering. Crab submarine engines don't burn fuel at a constant rate. Instead, each change of one step in horizontal position costs 1 more unit of fuel than the last. First step costs 1, second costs 2, third costs 3, and so on. So the moving further becomes more expensive. Okay. So I think we just need to modify this to change the fuel for target function, and that should give us what we need. I'm going to take out some of these, well, at least the min and max parts, but I'm going to go ahead and keep printing target. I'm going to go ahead and make a quick commit with part 1 solutions. And I'm going to go ahead and copy part 1, the source code for part 1 to part 2. And then we'll go ahead and work on changing this total fuel thing. So, so the total fuel cost is just going to be the sum of all the integers up to the difference in position. So we'll say, you know, distance is still equal to that absolute value, and the sum of integers from 1 to n, the formula for that is n times n plus 1 over 2. So we'll add distance times distance plus 1, and then divide by 2. So if we do that, and then we'll make a build target for part 2 here. And we will go ahead and run the part 2 program for the test input. And that gives us a target of 5 with 168 for the fuel, which agrees with what's said on the website. So let's do it for our actual puzzle input. Okay. Lot more fuel. Let's see if that's correct. All right, we got it. So let's see, just out of curiosity, where our stats were. Oh my, internal server error. Yikes. I guess we may not be able to find out what our personal stats are for tonight. But nevertheless, we got the right answer there. I think the only thing, well, okay, what slowed us down tonight? Two things, I think. One was trying to be a little too clever, and my mathematical intuition was that the average position would be the cheapest overall for everything to move to. That was not correct. Um, and the other thing was I was using min and max instead of min element and max element here. That is a tricky thing that I should have remembered, but basically, um, min and max in the C++ standard library will just, compare their arguments exactly as is. Um, for iterators, like we get from positions.begin and positions.end, those are random access iterators on a vector, and they're comparable just like integers. So the first iterator in position, not in value, but just in its position, so begin would be the minimum, and the last iterator in position, end, would be the maximum. Now, with min element and max element, what it does is it will actually compare the iterators in a range. So not just those elements, but all the positions in that range from begin to end. And it will compare them by dereferencing them to take their value. So that was that was kind of what slowed me down for the first part. But the second part really was a pretty simple modification of the first part. All that we needed to do was just change the way that we compute the fuel, and it's not all that more complicated than the first part. And our brute force search for all the possible target positions turned out to be fine. And yeah, I mean, there were only a couple of thousand target positions anyway, so I guess, computers are happy to do all that brute force work for you. So didn't have to do anything algorithmically any more fancy than that. So yeah, pretty happy with the solution here. And oh man, now we're getting a "this page has been temporarily disabled" message for personal stats. So who knows how well we did tonight, but I guess I'll let you know at tomorrow night's stream. So thank you everyone for watching. Once again, if you are watching this on Twitch, you can find links to replays on my YouTube channel and the code in my GitHub repository in my channel profile. If you're watching this on YouTube, you can find links to the Twitch live streams and once again to that GitHub repo down in the video description. So thanks again for watching. I will see you tomorrow night. Bye-bye.